Hi, I'm Mark Barsamian. In this video, we're going to continue considering limits from an analytical perspective. That is to say, limits where the function f of x is given by a formula. And in particular, in this video, we're going to be considering limits of what are called piecewise-defined functions. The tools that we will use are, again, the theorems involving facts about limits that we used in the previous video. That is Theorem 2, Properties of Limits, and Theorem 3, Limits of Polynomial and Rational Functions. First example, f of x is this function here, involving a single bracket and two lines of formulas. We're supposed to find f of 3. We're supposed to find the limit as x approaches 3 from the left of f of x, the limit as x approaches 3 from the right of f of x, and the limit as x approaches 3. Well, we have to start by making sure that we understand what's meant by that notation. This example is what's called a piecewise-defined function. That is, it's described by different formulas on different pieces of its domain. The notation is very much abbreviated. To understand how the function actually works, it's helpful to think of it in a less abbreviated form. So I'll write that less abbreviated form here. I'm going to write it on 2 lines. So this very terse symbol for the function actually stands for these 2 sentences, 2 different sentences describing how the function behaves on different parts of its domain. Now, it's even more helpful to think of a function in the form that reflects how you actually use the function. So that is, when you're given an input x, you first have to figure out what piece of the domain that x is in, and then use the appropriate formula to figure out the y value. So that process could be better described with sentences written in the following way. So if x is less than or equal to 3, then f of x is given by this formula, and if x is greater than 3, then f of x is given by this formula. All right, now we're ready to solve the problem. To compute f of 3, we first note that because this inequality is true, we use this formula to compute the y value. So we get a result of f of 3 equals 4. And let's be very clear in our computation to explain why we did what we did. So we chose the appropriate formula for the function, and we substituted in x equals 3 into that formula. All right, now we're supposed to find the limit as x approaches 3 from the left of f of x. Well, notice that this symbol, x arrow 3 superscript minus sign, tells us that we should be considering x values that are getting closer and closer to 3, but less than 3. Well, for those x values, the relevant formula is f of x equals minus 2x plus 10. So when we compute the limit, that's the formula that we should use. So let's do the limit computation. So again, what we just did is we replaced the symbol f of x with the formula for f of x, but we chose the correct formula. We chose the appropriate formula. We should write that in. Okay, where do we go from here? Well, notice that we have a polynomial function. And remember that one of our tools is that Theorem 3 that says the limit of a polynomial function can be computed by just simply substituting in the x value. So we'll do that here, and we'll write down that that's what we did. Now notice that when I substituted in, I just substituted in the number 3. I don't do anything with this little superscript minus sign. I just substitute in the number 3, and so the result is the number 4. All right, now let's do the limit as x approaches 3 from the right of f of x. So since we've got this symbol x arrow 3 superscript, that means that we should be using x values that are close to 3 but greater than 3. So for those x values, the formula that we use for the function is that formula, f of x equals x squared. So the limit computation looks like this. So again, we first wrote down the expression that we were being asked to compute. That was this thing. We replaced it with this expression, which is the limit of f of x, but using the appropriate formula for f of x. And we had to figure out what the appropriate formula was. Since we were doing the limit from the right, the appropriate formula was f of x equals x squared. Once we get to here, then we just have a regular old limit. It happens to be a limit of a polynomial, so we used theorem 3, and that told us that we could just simply substitute in the x value, so we get the number 9. All right, well, the limit, the unrestricted limit, that is two-sided limit, is straightforward. Because these two left and right limits don't match, notice that the limit in question B was the number 4, the limit in question C was the number 9, so for question D we say that the limit does not exist because the left and right limits don't match. All right, question E says draw the graph of f, and so to do that, we should first draw separate graphs for each of the formulas that make up the description of f of x, and then use these separate graphs to build a graph of f of x. So remember that f of x had two functions involved in its description. One was this function, f of x equals minus 2x plus 10. The other function was this function, f of x equals x squared. So let's graph those functions separately first. F of x equals minus 2x plus 10, and f of x equals x squared. This graph is going to be a line with slope minus 2 and y-intercept at the point 0, 10. Now we can figure out the x-intercept of that graph. Because the slope is negative 2, the x-intercept will be at 5, 0. So that's the graph of that function. The other graph that's involved in the description of f of x is the function f of x equals x squared. That's a standard parabola. Remember that this parabola has a vertex at 0, 0 and goes through 1, 1 and negative 1, 1. Now, what are we supposed to do with these things? Well, remember the description of the function f of x is that for x's to the left of the number 3, we use the straight line formula to build the graph of f, and when x is greater than 3, we use the parabola formula to build a graph, the graph of f. So it should be well, it will be useful for us to know what happens on these graphs when x equals 3. So this graph goes through the point 3, 4. This graph goes through the point 3, 9. All right, so we have to build a graph of f of x by using the left chunk of this graph to the left of x equals 3, and the right chunk of this graph to the right of x equals 3. So when we build the graph of f, it's going to look like this. Straight line coming down through the point 0, 10 and including the point 3, 4. So the graph includes this point. Now, so that's what happens to the left of x equals 3 and right at x equals 3. To the right of x equals 3, we're supposed to use the right chunk of this graph. So we have to do this carefully. We take a piece of that parabola. It starts way up here at 3, 9, and it's on its way up. It's already steep at that point, so I'm going to draw it very steeply. So this is the location 3, 9. But it's very important to draw attention to the fact that there is no point on the graph at that location. There can't be. You can't have two different y values at x equals 3. And notice, remember, in the function description, we're only supposed to use this formula, f of x equals x squared, when x is greater than 3. So the way that you graph this function is you grab that chunk of that parabola and you put an open circle on the right. So let's notice the sentence summaries like we did a couple of days ago when we were looking at limits of functions given by graphs. Let's consider what the sentence summary would be for this graph. So notice there's a point. There's a point at xy equals 3, 4. And then the graph is heading for the location 3, 4 from the left. And the graph is heading for this location 3, 9 from the right. So notice the limit does not exist when x equals 3, even though the y value does exist. When x equals 3, the y value is the number 4, but that's not the limit. The limit does not exist. All right, that's the end of that example. Let's go on to another example. Remember, the subject for today is limits involving piecewise-defined functions. All right, here's our function, f of x equals x minus 11 divided by the absolute value of the quantity x minus 11. We're supposed to find a y value, we're supposed to find a left limit, a right limit, and the two-sided limit, and we're supposed to illustrate with a graph. As with the previous example, it's important to understand what the notation means. Now, to start with, let's think about the absolute value function. Most of you are probably comfortable with what you know about the absolute value symbol. So, for instance, absolute value of 5 is 5, absolute value of negative 7 is 7, absolute value of 0 is 0. Well, in all three of those examples, there was an actual number inside. Most of you are probably not so familiar with the absolute value function in abstract settings, where the thing inside is a variable or involves a variable. So the absolute value symbol actually represents a piecewise defined function. Here it is. So here is that same kind of terse presentation of piecewise function that we ran across in the previous example. So as in that example, it's helpful to think about this function in a form that actually reflects how you would use the formula. So that's this form. That's the absolute value function in sentences. Now, to understand how the absolute value function is used when the thing inside is a more complicated expression, it's helpful to consider what I would call the empty version of the function. So we have these two sentences. Notice there's no x in these sentences. There's just a pair of parentheses. So the absolute value symbol means different things depending on whether the thing inside it is known to be positive or negative or 0. All right, well, so since the absolute value symbol represents a piecewise defined function, then the given one-line formula for f of x, that is this symbol, actually represents a piecewise defined function. So let's figure out how it behaves. If x is greater than 11, then then x minus 11 would be greater than 0. And so since the thing inside of these absolute values is greater than 0, then the absolute value of x minus 11 is just the same as x minus 11. So in this case, the expression for the function simplifies to the following. I can cancel x minus 11 over x minus 11 because I know that x minus 11 is not 0. An important theme in this course is going to be the issue of canceling. So we have to know that something is not 0 to know that we can divide it by itself and cancel. All right, now if x equals 11, then x minus 11 is the number 0. And so that would mean, in that case, x minus 11 absolute value would be absolute value of 0, which is just the number 0. And so in this case, the formula for f of x would simplify to, it doesn't really simplify, the symbols involved in the formula for f of x are actually the numbers 0 and 0, and so the function does not exist. The y value does not exist at that x value. Now, what about the case where x is less than 11? Well, if x is less than 11, then x minus 11 is less than 0. So that means that the absolute value of x minus 11 is computed by taking the negative of the quantity x minus 11. So this symbol, absolute value of x minus 11, that symbol actually represents negative parentheses x minus 11 if we know that x is less than 11. So in this case, the formula for f of x simplifies to the following. The numerator is x minus 11. And the denominator is the negative of x minus 11. And that's equal to negative 1. And we can cancel because we know that x minus 11 is not equal to 0. Summarizing what we just found, a sentence description of f of x would be the following. A more concise piecewise presentation would be the following. This is an abbreviation of those sentences. So our job was to, first of all, in question A, find f parentheses 11. So find f of 11. Well, let's go back up and look at what we just found for the description of how f of x behaves. If x is 11, then f of x does not exist. So our solution is, all right, question B, we're supposed to find the limit from the left, the limit as x approaches 11 from the left of f of x. So remember that symbol, x arrow 11 superscript minus sign, means that we're supposed to be considering x values that are less than 11. So for these x values, the formula for f of x is f of x equals negative 1. Remember the sentence description of the function f of x was this. When x is less than 11, when x is to the left of 11, f of x equals negative 1. So let's compute the limit. So as we did in the previous example for a piecewise defined function, when computing a one-sided limit, we start by picking out the correct formula to use for the function. Well, in this case, the formula is very simple. The formula for f of x is just f of x equals minus 1. Well, so how do you compute the limit of that? What's the limit of negative 1? Well, let's go back up and look at our limit properties. Limit property 1 says the limit of a constant k is just the number k. So the limit of a constant k is just that number k, whatever it is. So that's limit property 1, theorem 2.1. Now, our job is to find the limit as x approaches 11 from the right. Well, this symbol tells us that x values are greater than 11. So for these x values, the formula for f of x is f of x equals 1. So the limit from the right is computed this way. The limit is the number 1. So again, we used the correct formula for the function. We used the formula f of x equals 1. And then we used theorem 2.1. All right, now question D says find the two-sided limit. Well, notice that in question B, we found that the limit from the left was -1. In question C, we found the limit from the right is +1. So in question D, our answer is easy. Now, finally, illustrate with a graph. Now remember that the formula for the function is concisely written this way, but a sentence description is often more helpful. So here is the sentence description of how the graph has to behave. Well, we can make a graph that looks like that very simply. First, we draw the axes, and then we notice that an important x value is x equals 11. Now, at x equals 11, f of x has to be undefined. So I'm going to put a vertical dotted line here to illustrate or to indicate that we have to not have a y value when x is 11. But to the right of x equals 11, the y values have to equal 1. So my graph is going to look like this. And to the left of x equals 11, the y values have to equal -1. So the graph is going to have to look like this. Remember the limit behaviors. The limit from the right of 11, the limit as x approaches 11 from the right was the number 1, and the limit as x approaches 11 from the left was the number -1. Well, those limit behaviors, remember, have kind of sentence descriptions in terms of how the graph behaves. Notice that the graph So the graph is heading for the location xy equals 11, 1 from the right. That's the sentence description that corresponds to this limit sentence. Notice I said location, not point. There's no point at 11, 1. Now, the graph is heading for the location xy equals 11, -1 from the left. So again, I said location. There's no point at that location. There's just a hole. All right, that's the end of this video. Thank you.